Hey guys, in this video we will be talking about the first of three bonding types, covalent bonding. After this we'll be talking about ionic bonding and metallic bonding. We hope you enjoy the video and remember to stay sciencey. Now let's start by refreshing the Bohr model of the atom. The atoms are arranged with a nucleus and several shells containing a set number of electrons. Now if we take chlorine for example, the innermost shell has 2 electrons, followed by 8, followed by 7. Now if they can be arranged in pairs, they are arranged in pairs. For the purposes of covalent bonding, we only need to worry about the outermost shell. So if we redraw chlorine, we have 7 electrons around, which we will be focusing on. Now a covalent bond is just a pair of electrons being shared between 2 atoms. If we take a chlorine molecule, Cl2, we can represent this bond by the grey stick, essentially representing 2 electrons that are being shared. We can also display covalent bonds using dot-cross diagrams. Now a dot-cross diagram of that chlorine molecule would look like this. The dots represent the electrons in the outer shell of the chlorine on the left and the crosses of the chlorine on the right. Right here in the middle you see where the electrons are being shared. Now this is a water molecule which you may recognise from our logo. Now using the periodic table we can predict how many electrons are meant to be in the outer shell of each element. Oxygen, represented by red here, is in the 6th period and it naturally has 6 electrons in its outer shell. Hydrogen has 1 in its outer shell. Using a dot-cross diagram, this is what water will look like. Here we can see 6 dots from the oxygen and 2 crosses, 1 from each hydrogen. You may also notice that oxygen now has 8 electrons around it. In covalent bonding, you tend to try and fill the outer shell to its maximum capacity. Oxygen's outer shell has a maximum capacity of 8 electrons, hydrogen's has a maximum capacity of 2, because its outer shell is the innermost shell on most atoms. Another example would be ammonia, NH3. Here we can see 5 dots around the nitrogen and 3 crosses, 1 from each hydrogen, filling all their respective shells. Now you may notice oxygen has 2 grey sticks representing a double bond, 2 distinct bonds or pairs of electrons. With a dot-cross diagram you can see this a little more clearly, with the dots from the oxygen on the right and the crosses from the oxygen on the left. There are 2 pairs of electrons down the middle, representing the double bond, as opposed to a single bond. Carbon dioxide, like oxygen, has double bonds as well. And we can represent this, again, with a dot-cross diagram, showing 2 lots of double bonds. Covalent bonds are very strong. However, the forces of attraction between simple covalent molecules tends to be quite weak. This explains why they tend to have quite low boiling points, as not much energy is required to separate these forces of attraction and allow them to change state. As well as simple covalent molecules, we can also have giant covalent lattices. Take carbon. Now carbon in this arrangement can form a giant covalent lattice known as diamond. Another giant covalent lattice you may be familiar with is silica, or silicon dioxide, the primary component of sand. Now, giant covalent lattices don't have a molecular formula as there's no set amount of atoms within the lattice. However, they do often have ratios between the atoms, so we can represent them by that. Silica we represent by SiO2, as is a 1:2 ratio. Diamond we just represent as C, as it is just carbon by itself. Now these lattices will have very high boiling points, as the covalent bonds between the atoms are very strong, as I previously said, and there's no weak intermolecular forces between the molecules because they are not molecules. Now that's it for today, folks. Hope you enjoyed this video, look out for the next two, and remember to stay sciencey.